Okay, so you have probably received the email about what will be contained in the exam. So we have already covered all those topics. So today I'm planning to solve some example problems. Now, do you have any questions that you would like us to solve? Okay. Can you describe it? Describe it.
Şurada RC şeylerinde hocam R'yi alıyoruz ya. R'yi neye göre alıyoruz devrede? Yani mesela burada bunu almış, burada bunu almış.
Well, let's solve it. Now, it's an application of the Kirchhoff's rules. So we have a circuit. There is one EMF source here with an EMF of V, a resistance R, and connected to those another resistance 2R. And in between there is a capacitor here. No, here there is another resistor of resistance R. Here there is a capacitor with capacitance 2C. This is plus Q minus Q2. Here there is another capacitor. Capacitance C, this is plus Q1, the other plate is minus Q1. So the question, there is a switch over here, then at t is equal to 0, both capacitors are empty, the switch is closed, so we have this circuit. And then you just wait. Wait until all the capacitors are completely full. Then the question asks, how much charge does each capacitor have as t goes to infinity? And what is the potential across the capacitors? And which point has a higher potential? So what would you suggest? What happens at t goes to infinity? What can you say? Well, the capacitors are completely filled, so there is no current running through this wire and neither through that wire. So they are as if they don't exist in the circuit. So you can just ignore them. Well, if you ignore them, this is what you get. This is the remaining circuit. This is it. And let's see, this is V, this is R, this is 2R, this is R. What is the current running through the capacitor? Well, the equivalent resistance is 2R, 3R, 4R. The potential is V over 4R. Let me give some names here. This is the point A, this is the point B, this is the point C. What is the potential difference between the point A and B? Between these 2 points? Well, it's the potential difference is just the resistance, which is 2R, times the current is 2R V over 4R or V over 2. Now, what is the potential difference between a B and C? Well, it's just, again, the resistance multiplied by the current. So the resistance is R, current is V over 4R, so VBC is V over 4. Well, those A, B, and C's are these points over here. Now, what is the potential difference across this capacitor And in terms of this VAB, VAC, VBC, well, first let's see what it is. So the potential is just VAC. You see this point and this point, since there is no resistance here, they are at the same potential. And this point and all the way here, this point, they are at the same potential because there is no resistance along that line. So this, on one hand, we know that it's Q1 over C, the potential difference. If the charge is Q1, the capacitance is C, then it's just Q1 over C. On the other hand, this is just VAC, which is V over 2. Now VAC is VAB plus VBC. It's just 3V over 4. So we know Q1. Q1 is 3 over 4 CV. What is the potential difference across this capacitor? It's just VBC. Well, it's just Q2 over C. This is equal to VBC, which is just V over 4. So Q2 is 1 over 4 times CV. Now let's look at this capacitor again. Which plate has the positive charge? The left one or the right one? Well, the left one. The current is coming from here, positive charges, they reach here. So the left one is positively charged. In this plate, the up one, the positive charges are coming here. Here you get the positive charge. Oh, you are right, sorry. The capacitance over here is 2C. So Q2 is 1 over 2 CV. Thank you. Okay, so it's always a Kirchhoff's. Again, we have a circuit. One resistor here, a capacitor here, an EMF source here, another resistor, another one, another EMF source. This is R1, this is R2, this is R3. This one has EMF epsilon, this one has EMF twice epsilon, this has capacitance C. There are also the numerical values. So, part 1A. At time t is equal to 0, the capacitor acts like, A is find the electric potential difference. So you have these 2 points, A, this is point B, this is point A. So you are required to find VA minus VB at t is equal to 0 and t is equal to infinity. No, one of them is A. Now let's start with at t is equal to 0. What happens at t equal to 0 to the capacitors? it's just as if it doesn't exist because it doesn't create any potential difference. It doesn't influence the current at t equal to 0 since it is uncharged. So we can just imagine at t equal to 0, the circuit would be just like this one. This is the point A. We have the resistance R2, the EMF source twice epsilon. This is the point B. We have another resistance R1, the point A. And here, epsilon R3. So this is our circuit at A is equal to, T is equal to 0. Now we need to find this, we need to find the current running through this wire. How do you propose we proceed? Well, we can use the Kirchhoff's rule. Well, let's see. We can go around this loop, and we can go around, let's say, this loop. We have those two loops. Let me give the names to the currents. This current, let me call it I1. This current, let me call I2. And this one is just I1 plus I2. Let me not give it a different name. So I have two currents, one running through this wire, one running from the above wire. Now the small loop would just tell me if I write the, let's say, potential increases, 2 epsilon minus I2 R2 minus I1 plus I2 R1, this is equal to 0. Do you agree? Anybody who has any problems writing such a loop rule for the Kirchhoff's rules? Any problem writing this line? Okay, for the larger loop, we have epsilon minus I1 R3 minus I1 plus I2 times R1. This is equal to 0. So we have two equations for the two unknowns, I1 and I2. We need to solve them. Well, let's see. The first equation is 2 epsilon minus I2 times R1 plus R2 minus I1 R1. The second equation is epsilon minus I1 times R1 plus R3 minus I2 R1. These are equal to 0. What we can do is just eventually we are interested in I2. Because if we obtain I2, the potential difference between A and B will be just 2 epsilon minus I2 times R2. That is what we are looking for. Well, let's eliminate I1. The first equation tells me that I1 is 2 epsilon over R1 minus I2 times 1 plus R2 over R1. This is my first equation. And if I substitute it into the second equation, epsilon minus 2 epsilon over R1 minus I2 1 plus R2 over R1 minus I2 times R1. This is equal to 0. Okay, let's solve it. This is, now here there is also another factor of R1 plus R3. Okay, so you can solve this equation for I2. Now, once you obtain I2, you see the question asks VA minus VB. Let's start from B and write the potential increases from B to A. Well, across the battery, the potential increase is twice epsilon minus I2 times R2. Well, okay, if you don't want to deal with the Kirchhoff's rules, if you solve it, most probably what you will get is I2 is just twice epsilon over R1 plus R2, and I1 is epsilon over R1 plus R3. So this is probably what you will get. Basically, here there is one circuit kind of independent of the other ones. This will provide a current I2 given by twice epsilon divided by the total resistance. This provides a current epsilon divided by the total resistance. Here the total currents will be added, so you get the I1 plus I2.
Is the current that refers to epsilon? It's the current's direction that refers to epsilon. Does it matter or?
It doesn't matter. If you assume the wrong direction, the current will turn out to be negative. If it turns out to be negative, then you know that its direction is the other way around. This is part A. Okay, not yet complete. Now let's look at what happens at t equal to infinity. Now this was our initial circuit. Well, at t equal to infinity, there is no current running through here. Just ignore it. So we only have these two. So one battery is trying to run the current in one direction, the other one the other way around. So the total EMF would be just epsilon. The total resistance is R2 plus R3. So this is the current running through the loop in this case. And the potential difference, VA minus VB, would be just 2 epsilon minus epsilon over R2 plus R3 times R2. Any questions on these two? Now let's come to part B. Now in part B, we are required to find I1 of t. Now this time as a function of time, not at t equal to 0, not at t is equal to infinity. So let me look up the circuit again. This is our circuit. So let's write the currents. Oh, already in the question it is given. This is I3. This is I2. And this is I1. And those are the currents we have. Well, this time there won't be any shortcuts. We have to write down the Kirchhoff's equation using the capacitor also. Let's start from point B. As we go from point B to point A, what are the potential increases? Or across the battery, what is the potential increase? 2 epsilon. Across the resistance, what is the potential increase? Minus I2 R2. Across the resistance R1, what is the potential increase? Minus I1 R1. Let's give the names to the charges. This is, let's say, plus Q. This is minus Q. What is the potential increase as we cross the capacitor? The potential difference is Q over C across the capacitor, and it's dropping because we are going from the positive plate to the negative plate, and this should be 0. Yes. Which one? Yeah, you can. No problem. Okay, as you wish. It will, the function will be with a minus sign. But even since you have changed it here, the physical situation will be exactly the same. You see, these choices, which direction of the current to choose as the positive direction, up to you. Which plate to denote as the positive plate, up to you. The important thing is how you interpret your final result. For example, if your results tell me that this plate will be negatively charged at some time, then whatever your convention is, this plate should be negatively charged at that time. Well, okay, let's look at the second loop. Let's go start from B to A again, but go the other way around. Let's write the potential increases. The first two terms are the same. Now, what is the potential increase across the resistance R3? It's just I3 times R3. What is the potential increase across this battery? Minus epsilon. This should be 0. What else do we have? At the point A, what does the junction rule tell us about the I1, I2, and I3? How are they related? So ingoing current is I2. So the I2 current carries charges to the point A. I1 and I3, they move it away. So I1 plus I3 should be equal to I2. And finally, how can we relate I1 to Q? Well, I1 is just dq over dt. Plus or negative? Minus. Let's see, if I1 is a positive current, does Q increase or decrease? So if I1 is positive, Q should increase. Well, increase means its derivative is positive. So if I1 is positive, the derivative should also be positive. So the signs are correct. If, for example, as your friend had suggested before, if we had chosen this plate to be positive, the lower plate to be positive, upper plate to be negative, when I1 is positive, then the charge in the plate should decrease. That is, when I1 is positive, dq by dt should be negative, and then we should have a minus sign over here. Yes, that sign over there becomes positive, but now that sign moves over here. We have a minus sign over here. So we have 4 equations and 4 unknowns. And what we need to find is I1. What would you propose we should do?
So we will combine the third and second equations.
Okay.
So we'll find I, because all of that one is I2 and
Hmm?
it's the wrong way.
Well, I just feel lazy to solve it, to be honest. At the end of the day, the rest is just solving the algebraic equations. Then you get a differential equation, though. You see, what I would do is I would first convert everything in terms of Q, in terms of the charge. So what that will give me, let's see, I want to find I1. Using this equation, I can write everything in terms of, I can convert I2 to the others, twice epsilon minus I1 plus I3 R2 minus I1 R1 minus Q over C is equal to 0, and 2 epsilon minus I1 plus I3 R2 minus I3 R3. Now this is just epsilon equals 0. So I now use this equation. Now, among these two equations, I have to eliminate I3. So I3 is, well, let me just use this one to solve for I3. That equation tells me that I3 is epsilon minus I1 R2 divided by R2 plus R3. This equation. So it's just, this is epsilon minus I1 R2 is independent of I3. Here we have the I3 terms. The coefficient is R2 plus R3. Now I can put that I3 in the first equation. So I will get an equation that relates I1 and Q. So 2 epsilon minus I1 plus epsilon minus I1 R2 over R2 plus R3 times R2 minus I1 R1 minus Q over C, this is equal to 0. What I did was I already solved for I3. I put it in the first line, so this is what I have. Now let me simplify this a bit. What I would like to do is, you see, there are terms that are independent of I1, like 2 epsilon over here, this epsilon term over here is independent of I1 and Q. Let me separate them. 2 epsilon minus epsilon R2 over R2 plus R3. Then there are terms that depend on I1, like this one, and that one. Let me write those terms. Minus I1 times 1 plus 1 minus R2 over R2 plus R3 times R2. That is this term and this term. And then I have minus I1 R1. Then minus Q over C, this is equal to 0. We have, let me now simplify it even further. Twice R2 plus, no, R2 plus twice R3, the first parentheses, minus I1, this is R2, R3, divided by R2 plus R3, plus R1, minus Q over C, this is equal to 0. Well, let me just give these some names, A, B, and C. Now, this is A, and this is B. So the equation we have is A minus B times I1 minus Q over C is equal to 0, or A is equal to B times dQ by dt plus Q over C. Now we need to solve this equation. Now that equation I can write in this form: A minus Q over C is equal to B times dQ over dt, or dt is equal to B over A minus Q over C times dQ. Now I can integrate it from t equal to 0 up to some finite t, from 0 to q of t. So t would be equal to b times the logarithm of a minus q over c multiplied with minus c. Q is equal to 0 to q is equal to q of t. So this is minus b c logarithm of a minus q of t over c divided by a. Okay, this equation will give us the q. And well, once you find the q, just take the derivative. I1 of t is equal to dq by dt. As I said, once you write the Kirchhoff's rules, the rest is algebra.
Şimdi bazen biz Kirchhoff'tan gidip devreye şey yapıp ulaşıyoruz. Bazen de direkt formülü yazıp çözüyoruz. Şimdi buna nasıl karar veriyoruz? Çünkü bazı sorularda herif yazmış işte bu en sondaki işte i eşittir e üzeri eksi t bölü rc yazmış, direkt yeni yazmış.
So that you also find from the Kirchhoffs.
İşte onu direkt yapsak olur mu?
That depends on the question.
Nasıl anlarız?
It should specify. You see, in the questions, it says that you should show your work. Now, what that means, of course, you don't start from, when we ask you some capacitor problem, you don't start from the electrostatics and explain everything, but you should show something that you understand where they come from.
So what do you suggest? Starting from the beginning or?
Which question is it? Well, you see, for example, let's go back. You see, what I did over here, I wrote just I is equal to epsilon over the total resistance, right? I just wrote the equation. No, I didn't write the equation directly. I first sketched this picture. And I explained to you where that circuit comes from. For example, if you would explain these, that should be enough. There is no computation here. The reasoning is at t equal to infinity, the capacitor doesn't allow any current to pass, so the circuit reduces to this one. Well, this is a simple circuit, and so you have that one. You see, what we would like to see is that you are actually understanding what you are doing, not just picking up random formulas. If you write enough to convince us that you know what you are doing, that should be enough. It doesn't have to be formulas, it can be sentences, it can be like circuits. Other questions? If you like, we can also repeat some topics. If there's any topics that's not clear to you. Well, you received the emails, I didn't. Well, let's see, I mean, that's kind of, but still, the idea is to learn. That's an earlier topic, so let's review. Here you have the dielectric. And let's say, without the dielectric, let's say this has the capacitance C. And then here you insert the dielectric. Well, the easiest way to solve this would be, we can just consider this as, first we can divide it horizontally. So we have two capacitors. And eventually the dielectric will be inserted over here. And what is the capacitance of the upper capacitor? This one? It is basically the same capacitor with the separation reduced by a factor of 2. It's 2C. This is 2C. Sorry. This has capacitance 2C. This has capacitance 2C. Do you agree? Now I will do one more step. I will divide the lower capacitor into two parts. You see, why did I do that? If you just imagine this surface over there, it has zero charge. Well, these two plates have a total of zero charge. And these two plates, since they are connected by a resistorless wire, they are always at the same potential. So if you compare this one and that one, the potential difference across these 2 points is equal to the potential difference across these 2 points. The potential difference across these 2 points is the potential difference across these 2 points. The potential difference across these 2 points is 0. The potential difference across these 2 points is 0. The two systems, for a given charge, well, they basically have the same potential differences across the plates. So that is why these two are equivalent. Now what I will do is, I will just divide that capacitor into two. Well, there is the upper capacitor, which is a capacitance 2C, and the lower capacitor I just divide into two. You see, in the original case, all of this plate is at the same potential. Well, over here also, everything is at the same potential because they are connected by resistorless wires. And what is the capacitance of this capacitor? So that the sum will have the total capacitance 2C. Well, this one has capacitance C. The other one has capacitance C. Now we insert the dielectric. Now the capacitance over there became kappa times C with the dielectric. Now I have two capacitors in parallel which are connected in series with a third capacitor. So what is the total capacitance? Well, what is the total capacitance of these two? Well, C plus Kc. So that circuit is actually the same as this one. Here we have a capacitance 2C. Here we have C plus C times 1 plus K. Well, vacuum corresponds to K is equal to 1. And when K is equal to 1, this and they are equal. And here we have two capacitors in series, which is equivalent to a single capacitor with capacitance given by 1 over 2c plus 1 over c times 1 plus k. Yes, other questions? So you have a circuit. So you have R1, R2, 1 ohm, 8 ohm, 2 ohm, 4 ohm, and here you have a capacitor with 1 microfarad. And they are all connected to a battery with V with an EMF of 10 volts. And this says that the circuit has been connected for a long time, that is t goes to infinity. And now nothing changes with time. The system had reached the steady state. And then it asks for, let's say this is point A, this is point B. What is VAB? Well, we know that a long time had passed, so the capacitor is now full. It doesn't allow any more current running through it. So this circuit is in fact equivalent to this one. Remove the capacitor, or remove the wires that have the capacitor, because no current will be passing through them. Now, what is the total resistance over here? 4 ohm, 1 ohm, 5 ohm. So this is equivalent to, here we have 5 ohm. And on the other side, what is the capacitance over here? What's the resistance over here? It's 10. Ohm. Now, what is the potential difference between those 2 points? 10 volts. What is the potential difference between across this resistor? 10 volts. So what is the current running through the resistance? 1 ampere. So this is 1 ampere. What is the potential difference across the other resistance? Potential difference is again 10 volts. The current running through that resistance, 2 amperes. Now let's go back to our initial circuit. Now we had already determined that here there is 1 ampere running, here there is 2 amperes running. Now let's see, what is the potential difference between A and B? Let's calculate the potential drops. Now from A to B, let's calculate potential increases. Well, from A to B, A to this point, what is the potential increase as we go from here to there? 2 ampere times 1 ohm is 2 volts. That is how much potential increased. And from here to here, how much did the potential increase? 8 ohm times 1 ampere is 8 volts minus 8 volts. Minus 6 volts. So VB minus VA is minus 6 volts.
So when it's in the steady state, we act like the capacitor doesn't exist. When it's in the steady state, we act like capacitor doesn't exist.
You see, what the steady state means is that your system doesn't change with time. Nothing changes with time. But if, for example, if there is current running through the capacitor, that means the charge is changing. So there cannot be, when it says steady state, it basically means that there cannot be any current running through the capacitor. The capacitor is at its maximum charge. Since there is no current running through it, I can just remove it. The currents will not change anywhere. So that's the crucial step. So what we did first, since it said that we are looking at t is equal to infinity, that circle is just equivalent to this one. And this one just tells me, by just calculating the equivalent resistance of both of these lines, we determined the currents running through both of these branches. So once we determine the currents, well, those branches are nothing but these branches over here. This 1 ampere just flows all the way through. This 2 ampere flows all the way through. None of them go through the capacitor. Now we can ask a similar question. What are the currents running through, let's say, this resistor and this resistor at t is equal to 0? Before it was the steady state. Now we can ask the question, if there is a switch over here, initially the capacitor is empty, what is the current running through these resistors when the switch is closed? An alternative question. So what is the crucial thing about when the switch is closed? There is no charge. So it is as if there is no capacitor there. It's just a short circuit. So that circuit is essentially this one. I have the battery here. Here I have 1 ohm, 8 ohm. 4 ohm. 2 ohm. At t equal to 0, this is my circuit. You see, this one over here is the line where there is the capacitor. It's the short circuit. Well, let's see. What is the total current? What is the resistance of these capacitors? These two. What's the total resistance of this part? 8 over 9. 1 over 8 plus 1 over 1 gives 1 over the resistance. That is 8 over 9. What about the other one? 4 over 3. Just multiply them, divide by their sum. Or let's say, okay, 4 over 3. So the total current running through the system would be 10 volts divided by 8 over 9 ohms plus 12 over 9 ohms. Or the current is 90 over 20 ampere, 9 over 2 amperes. That is the total current running through the circuit.
Hocam şimdi yukarıda burayı bizim short circuit oldu ya. Şimdi bu taraftan bir akım gelecek, diğer taraftan bir akım gelecek. Bunlar birbirini götürme durumu falan oluyor sanki, ben öyle hatırlıyorum ama. Bir akım düşmesi falan bir şey oluyor aradaki kablo olduğu zaman.
Well, let's see.
Direkt çünkü topladık şimdi. Hani ters geçen akımlar oldu bu sefer.
Okay, so?
Yani bir ayrılması lazım. Mesela diğer tarafta 2 amper geçti, öteki taraftan 1 amper geçti.
Let's see what will happen. Let's see what will happen. Let's continue along this line and let's see what is the current running through that capacitor. Now, the total current is 9/2 amperes. Now, let's go to this figure. So 9/2 amperes enters here. If 1 unit goes over this one, 8 units should go over this one. So half an ampere goes over the 8 ohms. So here we have 1/2 amperes, and the other way we have 4 amperes. So that if you just, the total current is 9/2 amperes, that's the total current, and the potential difference across this one is 4 ampere times 1 ohm, 4 volts. The potential difference across this one is half an ampere times 8 ohms, 4 volts, as it should be. Everything seems to be working fine. Now let's go over here. We have 9/2 amperes, and if 1 unit of current flows through this one, since this is twice that much, if 1 unit flows here, 2 units flows over there. So it's 3/2 amperes through here, and 3 amperes from here. So again, if you just multiply the resistance with the currents passing through them, the total potential difference is 6 volts. 6 volts here, 4 volts over here, then you get the total 10 volts. Now let's go back to the initial circuit. Now what did we discover? Across that resistance of 8 ohm, we have half an ampere. So that is half an ampere coming across this resistance. And across the 1 ohm resistance, we have 4 amperes. Now let's go to the other resistance. Now across the 4 ampere resistance, the current passing through is 3/2 amperes. Now across this 2 ohm resistance, the current is 3 amperes. 2 ohm resistance, we have 3 amperes. Now let's see, 4 amperes comes here through this resistance. Now only 3/2 amperes goes here. How much should go to the capacitor? Well, the remaining 5/2 amperes just goes to the resistor, the capacitor. Well, let's see, 5/2 amperes comes across the capacitor. 5/2 reaches over here. 1/2 ampere plus 5/2 amperes, it makes 3 amperes. So we have also the charge conservation everywhere. So we know how much, so we can tell that at t equal to 0, this plate will start charging positively and that plate will be start to charge negatively. Well, let's give a 10-minute break now, and then we can continue along with this question.